This is lecture 2, as shown on the screen. So, there aren't really very many applications of superconductivity that are three-dimensional. So this is sort of an obvious thing to say that it's 2D. And of course, a wire is 1D, so it's a bit silly, but I was told that the Center for Advanced 2D Materials really like 2D in the lecture, so I put it in. So if we're talking about applications, there's two kinds. There's low current and high current. So we'll start off with a low current, and we'll end up with a high current. No, I'm not going to cover every superconducting application, and I may not cover your favorite superconducting application. At least in the United States, I won't speak for Singapore, lots of people working in the field of applications of superconductivity have hypnotic powers. They go to the funding agency and they exert their hypnosis on the guy, and they get $10 or $20 million for doing this stupidest thing you can imagine. And they've been doing this since the middle 70s. I mean, there have been projects that you would just shake your head and say, that's not worth anything, but yet it gets funded. So knowledge marches forward, and you might ask, why is it, at least in the United States, there's so much federal funding for research? Because once upon a time, Albert Einstein wrote a letter to Franklin Delano Roosevelt and said, you should support the development of a nuclear bomb. It'll be very powerful. And Roosevelt said, okay, and he went all in. I mean, that project got everything you ever wanted. I worked at Los Alamos starting in '77, and they had drawers and cabinets full of expensive pieces of Teflon that no one in their right mind would ever have bought. But they had so much money they didn't know what to do with it. So they spent a lot of money on research for the Manhattan Project, and it worked. You know, the United States got a nuclear device that enabled them to end the war with less casualties than it would have been if they'd invaded the home islands. And ever thereafter, the federal government has been hypnotized that if they throw money at a problem, the scientists will come up with a solution and things will be good. Now, that's not true. Since 1945, the number of times that the federal government has thrown money at a problem and an application has come through as was planned for has been very seldom. But let's talk about the applications. The U.S. Navy has high-temperature superconductor applications. We'll talk about those. I'm pretty sure some of that gets classified because the last mention I can find of one of them is 9 years old, so I think it worked, and then after that there wasn't anything more published. I'm not really sure. But there's lots of applications out there. So the low current applications use the Josephson effect, so we have to learn about the Josephson effect. And we talked about this last time. It was Brian Josephson when he was a grad student. The DC Josephson effect, and I won't bore you with reading everything up there, but the DC Josephson effect is if you take two superconductors and some sort of insulating barrier, the phase on the left and the right are the coherence of the superconducting paired electrons, if you will, the phase in the quantum mechanical state are independent, and if you don't apply a junction, sort of surprisingly, a current flows, and when you make the barrier thin enough, obviously it has to be a single superconductor with a single phase. So the current that flows is proportional to the difference in the phases, and so even without an applied voltage, you get a current somewhere along this line. It's not determined, and above a certain applied critical voltage, they go into the normal state. So that's not what we're going to be talking about today. We're going to be talking about the AC Josephson effect. So above this critical voltage where you're getting ohmic behavior, as in V equal IR, Josephson predicted, and you have to admire the experimentalists because this was really hard to go and measure, and it took years. I think it was Shapiro that did it. he predicted in 1962 that in this ohmic regime, there would be an alternating current, supercurrent, of this frequency. And you'll very often see this written in the literature without the star. So it's a little confusing because you think it's 2 electron volts. No, it's 2 times the fundamental charge of an electron times the voltage that's in this graph, divided by the Planck's constant. So just to give you an idea of the scale, if this is only a few milli-electron volts, it's this relatively large frequency. Now maybe there are people in the room that are comfortable with gigahertz. In my lab, we would just be totally lost. But anyway, it's a very low power emitted signal, and eventually it was detected, and when you apply a voltage to that junction that we saw in the previous graph, you can adjust the phase difference via this relationship, and so you get a current that, if you weren't applying a voltage, would just be some constant number, and again, it's not determined what it is, because the difference in the phase between the 2 superconducting regions at t equals 0 would be just some number which wouldn't necessarily change with time. But when you put on a voltage, then you get this oscillatory behavior. And you can measure frequency very accurately. And so this Josephson frequency has become the basis of a voltage standard. So believe it or not, back in the 50s, 40s, the standard of voltage was some chemical wet cell, which was an enormous kludge and not very accurate. But now we have this huge accuracy, and I don't know if you guys know this, it used to be the National Bureau of Standards in the United States, and now it's called the National Institute of
Standards and Technology. Standards and Technology.
Yeah, that's what I think it was going to be, but I was waiting for him to correct me because it could have been something with standards. I don't know, but anyway, National Institute of Science and Technology, and it's you used to think that it was in Boulder, Colorado, but they also have an office back in Maryland. So it's never too hard for NIST to go do things. So they have 2,208 Josephson junctions in series, and they have a 10-volt standard, which sounds like a lot of work. And then the standard volt, the world over, is now defined as the voltage needed to produce a Josephson frequency of this, or if you're talking about a microvolt, it's a frequency like that. And so that enters into the science of metrology. There are, I believe, 7 or 8 fundamental constants that people that do metrology worry about. And in this year, but not yet, the world is switching over for their standard for a kilogram. So it's no longer this chunk of platinum iridium that sits in some vault in France. It's now going to be something involving scientific fundamental constants. So the science of metrology uses the Josephson effect to define the volt. And I'm sure that number is much larger than when I made this first talk up. So if you want to know what one of these things look like, here are 20,208 Josephson junctions making a 10-volt standard. Here is a machine that measures it. Now, of course, you have to have cooling because these are low-temperature superconductors. These are not high-temperature superconductors. And one of the things that is the ugly truth about Josephson junctions is they're thin films on substrates that don't thermally cycle well. So if you thermally cycle your Josephson junction a few thousand times, it will eventually crack and break. And I'll talk about that a little more later. So the next topic, still involving the Josephson effect. Suppose we take 2 Josephson junctions, there's one, and we talk about the phase difference going around the entire 360-degree of the loop. If you go clockwise, you get a phase difference of JA, and if you go counterclockwise, call it the phase difference for the current going in the B direction, call it the phase difference, delta B. So if you don't have any B field threading your area here between the Josephson the delta A and delta B have to be the same. And in the presence of a field, the difference in the phase is related to the fundamental flux quantum, which is some number like 10 to the minus 15 Webers. So again, the total current going around the loop is the sine of the sum of two parts and plus the sine of the difference between two parts. You use your trigonometric identity and you come out with this. So you have this constant term in front of it, and then you have this oscillatory term. And so here are various answers that you could get for the current as a function of magnetic field, and you see this oscillatory behavior. And so this is called a superconducting interferometer. Not what I want to focus on. If anybody wants to read up on this, there's a nice article way back when by Jack Levitch. And so this configuration of two junctions that was in the previous picture, then you have these two periodicities, one with delta naught and one with something involving the flux quantum here. And it's like, for anybody that teaches introductory physics, it's like a double-slit electron beam interference. And here is the answer for what a flux quantum is. And so you might ask, these Josephson devices, how low can they go? There's always noise in any physical measurement. I know theorists don't understand this part of the world, but there's always noise out there somewhere. So they could go down to a few flux quanta. Anybody that tells you they can measure one is probably not telling you the whole and entire truth. They make ultra-sensitive magnetometers for an application out of this. They've used these magnetometers for lots of things. The Navy uses them to look for enemy ships. People have used sensitive magnetometers around the pyramids looking for empty spots within the pyramid where secret treasure could be hidden, because of course the rock that the pyramids are made out of have some amount of susceptibility that you could then map out and look for places where there wasn't a contribution and there would be an empty space. The answer is no, there are no unfound chambers in the large pyramids in Egypt, but they went and looked anyway. And so here is a picture in a more physical sense of what this might look at. So you have flux lines, which we talked about last time, threading the two Josephson junctions, and it's called a SQUID, a superconducting quantum interference device. So if you put a biasing current in the previous picture, the measured voltage that you get oscillates with the change in phase. We saw this a few slides earlier, and that depends upon the change in the magnetic flux. So if you put another quantum in, the voltage goes through this loop here, and so that corresponds to a change of one flux quantum through the Josephson junction. And so if I'm constantly increasing the flux, this is what my voltage as a function of time looks like. It varies as a cosine of the number of flux quanta there with some fundamental constants thrown in. There are, of course, technical issues, which I won't spend any time on, having to do with making two Josephson junctions in a SQUID geometry actually be able to see the magnetic signal. So they have pickup loops and gradiometers for feeding the magnetic flux lines into the SQUID device. Here are what some of them look at. These are very old pictures. So we had a SQUID magnetometer that was purchased from Quantum Design, which we bought in 1986. Magnetic property measurement system. We bought the fifth one that Quantum Design ever built. And within about 10 years, the SQUID broke. And the machine originally cost $150,000, and the price for a new SQUID install, we would ship the guts back and they would install the new SQUID and return it to us, was $40,000. So this piece of equipment sits sits in my laboratory unused, and we use one down the hall because we didn't have $40,000 spare outside of the startup money that I began with. There are probably over 1,000 of these in existence. It's amazing how much money laboratories have. Joe Thompson's group in Los Alamos, I believe, has 3 of these. They have since graduated from magnetic properties to physical properties. So there's such a thing as a PPMS measurement system, and you can now do things like specific heat, which has led to some amount of confusion in the literature because Quantum Design in San Diego, the company, tries to convince people that buy the machine, oh, don't worry, it's all automated, just put the sample in, the data will come out, you'll be fine. And of course, people don't understand what they're measuring, and so they publish wrong things, which sometimes winds up on my desk. So, just because someone gives you an automated machine to measure some physical property doesn't mean, and I hope this is being recorded and sent to the world, doesn't mean that you understand the physical measurement involved. This is my way of saying we're now going to change the subject. And so last time someone asked, I made this statement about a higher critical magnetic field. Someone asked about that. So it turns out that that's a superconducting layer with a coherence length depth. And you can get critical fields in that geometry where the field is parallel to the surface. And you don't have to worry so much about the radius of curvature as long as it's a few multiples of the coherence length. And, according to the superconductor, it looks like the field is parallel to the surface. But you can get up to some multiple of the upper critical field. And you can use that to do interesting high field things. And it's known as HC3. Okay, so there are new pedestrian lanes in China, which are called, they're dedicated to the head-down tribe. And you all recognize this in yourselves. You're walking along, doing your electronics, your head is down. And so the head-down tribe lanes are for people who don't watch where they go, and they just sort of like a bunch of cows move along in some constant direction and try not to bump into each other. So I wear a watch, but sometimes when I ask someone what time it is, it's amazing. I gave someone our phone number the other night, and I said, do you have something to write with? Well, of course, I'm an old guy. No one writes down a phone number. She whipped out her cell phone and typed it in. Saved a step, right? Write it down on a piece of paper, then you have to call it in. It's all fine. So what you don't know is high temperature superconductivity is making your life better with your cell phone, which we'll now learn about. So really, I've just picked a few applications. There are a zillion applications. Smart people who want to make $1, an euro, a zloty, whatever, they're out there working along. So here's a schematic of what a cell phone area might look like. This number keeps going up. There are now more than 10,000 of these noise filters in operation. They have many advantages. They last a long time. They're relatively cheap. They do an amazing job of filtering noise, an amazing job. And we'll look at this bandpass data a little more thoroughly a little bit later. And it's done by a company, called Superconductor Technologies, which might be based in Austin, Texas these days, but I believe started in Santa Barbara. They had as an original member of their advisory team, John Clark, who's Mr. Josephson Junction at Berkeley. If you ever have a question and you can get him to answer your email, he's the guy to ask. He knows everything there ever was to know. And he's so theoretically oriented and so theoretically smart. I one time insulted him when I said, John, are you a theorist? He's actually an experimentalist, but it's okay. So this is sort of accepted. It's obviously in microscopic form. This is more or less their advertising. I would never write in a slide exceptional selectivity. This is their advertising, so I just copied it. So, so obviously, it's sitting at room temperature up on some cell phone tower, and obviously we don't quite have room temperature superconductivity yet. So they use things that have critical temperatures above 77, but they still need to cool it. So they have cryocoolers, and the technology here is amazing, and it works very fine. Here's a bunch more of advertising, but it is true that when you're talking about radio frequencies, you're no longer talking about a DC current through a superconductor that has no losses. Remember, we talked about the flux lines, we talked about high temperature superconductivity, not having a frozen flux lattice just below TC, but that is a liquid, so that flux lines can move around. If you have flux line motion, you have losses, energetic losses, right? There's a force times a distance, it doesn't work, there's an energy loss. So as soon as you put AC current into a superconductor, you're going to get, depending on what kind of superconductor you have, but certainly if you use a high temperature superconductor, you're going to get a lot of flux line motion. When we at the University of Florida were involved in making materials, the standard for whether a material was superconducting or not was the resistance fell below 1 microohm centimeter. That's not very good. Kimberly noticed did better than that in 1911. So the high temperature superconductors are not lossless, particularly if you do AC. So if you're doing AC high temperature superconductors and you have a cryocooler, it's got to carry some energy away. Okay, you just can't say, well, I need it, there's a very low heat load. It's a superconductor. No, it's not for AC current. So, again, this is just advertising a viable industrial technology, which is what you guys here in US want to do. You want a viable industrial technology, you want to have your own startup company, you want to go out and you want to make millions. There you go. So, this is a little bit back to the materials side of what I'm interested in. So, people use the yttrium, barium, copper oxide. People also use the thallium-based higher temperature, I think this is like 138 or something, superconductor. There's a technical term for this in the superconducting community. The thallium-based compounds are known as superconducting rat poison, because thallium is an important component in rat poison and very poisonous. You do not want to put thallium into your MBE. So if you have some wild character who's using your common facility down there, and they write a proposal saying, I would like to use thallium in here, make sure they're fired. Because you don't want to die. Thallium's really very toxic. We work with beryllium in my laboratory. Beryllium is a pussycat compared to thallium. You do not want that. Anyway, so you want C-axis normal, so you want the film this way, and you want the C-axis normal to it to get the low radio frequency losses that you're going to need. This is an old slide. They've got new substrates that I don't know about, probably some of which are proprietary and secret. And all of these substrates have all problems. And they're making rather large material these days. They have lots of different methods, and again, I'm probably 10 years out of date. So one of the methods for making materials, whether it be a high temperature superconductor, film, or something else, that I've always found very interesting is pulsed laser deposition, or PLD. You take a target of whatever it is you want to make a film out of, and you blast it with a laser pulse, which means you blow off physically, not atomic material, but you blow off pieces of the material that are actually larger than a unit cell. They're actually physically, in extent, not just atomic size, and you blow these pieces down on a substrate, which if you heat the substrate, you can manage to have these pieces form a rather nice film together. You can make diamond, you can grow diamond this way, you can grow diamond films with pulse laser deposition. And you wouldn't think you could, you'd think it would be a very dirty, messy process, but in fact it works. And you can do chemical vapor deposition, and etc. Sputtering is also popular. There's the problem that you need a rather high substrate temperature, and you don't want interdiffusion between your substrate and your film, because then you'll just get dirt in there, and it won't be a good superconductor. The other problem you need is, this is a very often not covered topic, but the good TCs are an oxygen of 6.9 and higher. So you really need to work at getting the right oxygen stoichiometry here. If you make a poor film, you know, the oxygen might be 6.3, 6.5, and the superconducting properties are poor. So you need to get the oxygen concentration up. And one of the ways, and again, this is 10 years out of date, is they have this spinning platter that spends most of its time under high pressure oxygen. And every once in a while, it goes through the area where you're evaporating the metallic constituents, and then it zooms back into the area where the oxygen is at high pressure, and you can actually grow the material. And this is sort of a little, you know, thinking about it, you'd say, really, that works? It's like pulse laser deposition. It didn't seem like it should, but it does. And this is this conducting company that we showed their filters from. So besides YBCO, you can also use the thallium-based, and that has various advantages. And of course, it has the extreme disadvantage that it's hard to make things containing thallium because the vapor pressure of thallium is so high. So what they do is they make everything besides the thallium, and then there's this new English verb, which I've never seen before. They thallinate the film by exposing it to thallium vapor pressure. Okay? So if anyone comes to your 2D laboratory downstairs or laboratory in physics and says, we'd like to thallinate something, be sure that the vacuum system that they're working in belongs to them forever. And if you can take out a life insurance policy on them, which is usually legal, you know, like if you see someone who's about to die, you write the insurance company and say, I'd like an insurance policy on this guy. They write you the insurance policy, you pay the premium, 30 days later he's busy thalinating and keels over. So, yeah, there's a lot of materials questions that you need to be careful. The first thing I teach someone that comes into my lab is, if you're working with a material, an element, a compound for the first time, what you do is you go look in this little red book. We have a little red book that lists all of those bad things, and they can read up on what the procedures are and how much in meter cubed of atmosphere they're allowed to have. So, you know, again, this is talking about electronics, which I understand very little of. Here's cellular and personal communication system applications. So they're just using these as an inductor. So here's, you know, they're talking about Chevy Chip bandpass filters. Again, I understand very little about this, but they have a very narrow bandpass. So, you know, this is 1 megahertz on full scale, and you see how narrow this is. So these are really, really useful for cell phone towers. So the only reason your cell phone is relatively noise-free and is so sensitive. I mean, it used to be, when I first started using a cell phone, if you went in the basement of a building, you were out of touch. Didn't matter who your provider was, you were out of touch. These days, you see people walking in the tunnels of the MRT and they're talking on their cell phone. And the only reason that works is the sensitivity is so high because they've got rid of the noise. If you had gone to that sensitivity without these noise filters, you wouldn't have had any improvement in your signal because the signal and noise would have been bad. So now we're switching to high current applications, which will end up the next half hour. Any questions on low current applications? Feel free to catch me after the talk. Okay. So there's some abbreviations that are common in the community. low temperature superconducting, high temperature superconducting. I was supposed to have filled this in. This is like 10.4. So anyway, niobium titanium is the material of choice for huge magnets because it's cheap, it's ductile, which means you can wind it easily and not take special care. And it's used for magnets up to around 9 Tesla. And of course, the A15 structure, iron 310, we discussed last time, these wires are, there's huge lengths of them produced in a year, and the high temperature superconducting wire is just coming online as we speak. So this is beginning to be commercial, but not quite yet. So this is for very limited application, because that's not very much material. And there's two kinds of high temperature superconducting wire, and I'm just telling you about first generation, which is really not much used anymore, to make you aware of how badly people wanted to make a high temperature superconducting wire. So it's called PIT, powder in tube. You take a tube out of silver, you put the powder in it, you then react it, and the silver is ductile, and you can draw the tube down to a wire diameter and make superconducting wire. Inside, of course, is this brittle high temperature superconductor, but it works, but it's horribly expensive. So that's first generation wire. So here's an understatement. The heavy reliance on silver made the wire far too expensive to commercially produce. So that's an understatement. Second generation wire, and they run into the problem here that the Chinese have flexed their muscles on supplying rare earths to the world market starting about 7-10 years ago, where they've started limiting the amount of rare earths they'll export. Now, it's not the case that there aren't a bunch of rare earths all over the world. It's not that China has the only rare earth mineral sources in the world. It's that the Chinese were willing to forego safety measures that the rest of the world insisted on. So their rare earths were cheaper because they didn't have the safety standards in place that made it very expensive to produce the rare earths from the alloy they were getting out of the ground. Okay, so since the Chinese have restricted export of rare earth materials to the world, obviously the price went up because, you know, supply and demand, it's scarce, and rare earths are used in automobiles. You know, the neodymium iron magnets, neodymium is a rare earth. So Detroit depended on exports from China of neodymium to make the magnets, to make the generators in the cars. And so this all got more expensive. So what that caused, of course, is everywhere in the world where there were known and proven rare earth reserves, companies suddenly woke up and said, I know, I can compete with the Chinese price and still have the safety standards that the local government requires. So I think we're back on track to having rare earths relatively accessible in the world market. And again, I'm not the world's expert. The only rare earths I buy are very high purity out of Ames Lab in Iowa, and those are so expensive. Those aren't commercially usable either. So the second generation uses rare earth barium copper oxide materials, and they're ramping up their productivity. There's still a cost issue because rare earths became expensive. Now, just to show you what the low temperature superconducting wire looks like, this is something you can physically see with your eye. And in one of these bundles, it looks like this. So here's a bunch of superconducting filaments. So this all starts off And it's a very tricky process, but people have been making A15 niobium tin wire for a very long time, and they have all the tricks figured out. Is when you draw the wire down, you can't have A15 material present because it's brittle. Except for niobium titanium, any superconductor you're going to talk about is brittle. They're all brittle. If you put them in a silver tube, okay, you can get away with it, but no one wants to do that commercially. So what they do is they draw niobium wire down in this rather complex geometry. This is just an expanded region here. So if you blow up these little things, that's these things. And so there's 13,000 filaments in this picture, and I once counted these. There's 20-some, I think. As soon as I say that, you'll correct me. But there's a lot of niobium wires here. And the niobium wires are in a bronze matrix. Bronze is copper and tin. You use the copper for thermal sinking of the wire in case you have a local fault where you have something go non-superconducting, and there's some joule heating. That heat gets carried away by the copper. So you have the copper present to give you some thermal stability, and normally 3 to 1 is a good ratio. And you might say, well, I'm losing, 75% of my current carrying capability per diameter wire because you insist that 3/4 of that wire be copper. Well, yes, but magnets made out of this stuff cost over $100,000, and if you have a failure where the wire breaks in one spot, in a magnet where you have maybe 10 miles of wire in there, the $100,000 magnet is trash, because you can't unwrap the magnet and go find the one spot where the wire melted through. So you need thermal stability, you need the 3/4 copper. But in the copper, which cuts down on its thermal stability properties, but in the copper is the tin part of the bronze. And so what you do is you draw the wire down, and you actually wrap it on the mandrel so it's in its curved form, because if you wrap niobium-3 tin in too short of a radius, it'll crack the A15 brittle structure as well. You wrap it on the magnet, and then you anneal it in an oven. And the tin and the niobium react. The tin comes out of the bronze, the niobium sits there, and if you do a good job, most of the cross-section of the niobium wire will turn into niobium-3 tin. And this is, of course, why they pay engineers the big bucks. Because, of course, the bigger the fraction of the niobium wire that you've done the annealing long enough till you get it as sort of a homogeneous cross-section that's mostly A15 niobium-3 tin, the bigger your current carrying capability is. Okay? So that's how you make a magnet using brittle wire. You don't allow the wire to be brittle until it's already in its final form. And then there's one further trick. If you do it right, you can put the wire under a little bit of stress when it cools, and TC goes up a little bit. So people are in there getting every 1/10 of a degree and every Tesla out of the critical field that they can. So there's a lot of tricks, some of which are proprietary. So here is the critical field. We've talked about this a little bit. This is all HC2. Here's the niobium titanium. You see it's got a critical field of maybe 13.5 Tesla at T = 0, which no one would ever run the magnet at. TC of almost 11 up here. And of course the material of choice is not labeled on, oh, here it is, here's niobium-3 tin. And so you might say, well, why aren't we using these other materials? There have been projects to make commercial length sections of niobium-3 germanium that never came to fruition. Anyway, just so you've seen it. The other important property, we're talking about critical temperature, we talked about critical field. The property that I haven't talked about much, of course, is the critical current. And this is a fair comparison of how these things look with respect to one another. Obviously, the critical current for niobium titanium is fairly small compared to the critical current for niobium-310. Now you might ask, where does the field come in here? Remember that when you put this much current through a wire, you're getting a self-field. So you can't run across the current in a solenoid configuration without getting a field. And so here's VSCO 2212, and you see that at higher fields, it maybe doesn't have the world's best critical current. It's still superconducting. So you can have VSCO magnets out to 30 Tesla. And we'll talk about this a little later. Cooling something below the lambda point of liquid helium 4 goes to a superfluid at 2.17 Kelvin. And cooling a magnet down below the superfluid point, like is shown here for these data, buys you something. But you only do it if you're desperate, because there's so much that can go wrong in your dewar if you have superfluid liquid helium-3 running around. And I will give you an example of desperation a little later in the talk. And it's the high energy guys. I mean, you'd expect it, right? They've got all these hundreds of millions of dollars to build their, all these billions of dollars to build their machines. They spend money like water. So here we go. The LHC, which we're all happy discovered the Higgs boson. We're all happy, you know. We're good with that. We're really, you know, that's where our tax dollars should be going. They use niobium ti, and they cool it to 1.9 Kelvin. And you might, if you remember your history, you might remember that when they first fired the LHC up, it broke. And I don't know if any of you know how it broke, but they had a helium vent from one of their magnets into their vacuum chamber, and it's very hard to whirl high energy particles around in a vacuum if it's full of helium gas. And so they actually had a failure in their cryogenic systems, and they just blew a bunch of helium. When the magnet quenched, it blew out a partition between it and the vacuum chamber, and it just flooded the LHC with helium gas. And then it took them 9 months to fix it. But, you know, you could have said, you know, guys, don't you think you should have a few low temperature engineers working for you if your entire system depends on running in superfluid helium? I mean, that's tricky, as they discovered to their chagrin, right? So if you're going to amortize the accelerator, let's suppose the accelerator lasts for 20 years, and let's suppose they lost a year of measurement time because of this mistake, and let's suppose it cost, I don't know, $10 million. You know, how many hundreds of millions of dollars was that mistake worth? It was worth a lot. But I don't think you can talk to those guys. And believe it or not, their next design, they're going to do niobium-310. So if you want a stock market tip, go find American Superconductor Corporation and buy. It's like $6.59 right now. When they get an order to make enough niobium-310 wire, because you know these guys have 30-mile rings, to put enough magnets around to bend particles into a circle, I mean they're going to be the world's wealthiest company. Now I don't know that American Superconductor will get it. I don't own stock in them. I don't have any financial interest. But when the high energy guys who manage to hypnotize the funding agencies routinely, when they do their next generation collider, and they're going to use niobium-310, because you know it's a charged particle, and a V cross B has to turn into a circle. It'll be impressive. So, has anybody in here never known someone that got an MRI? I mean, I've had an MRI. MRIs are sort of common. So it used to be that MRIs, well, let's see, that's the next slide. What is MRI? So it's because you've got water, and because in your water you've got hydrogen. So what they're doing is they're looking at the hydrogen nuclei. They're looking at the proton. It has a spin up and a spin down state, and I don't know if you've been lying in the MRI. And there's this humming sound. There's this repetitive. That doesn't sound like a DC field to me, and it's not. It's the RF. So they're busy pumping the protons up to the upper energy state, and then it gets quiet. Have you noticed when you're lying in the MRI and it went, and then suddenly they don't drag out, but suddenly it's quiet again. So that's what they're doing. When the RF is turned off, the population from the excited spin state, and it's just a proton. It's a spin up and a spin down. It's not complicated quantum physics. Decays, recesses to the lower energy state. And when it does that, it has to give up its energy, and so it emits RF, and that's what the machine detects. Okay? It's detecting your protons. And in popularized description, that's called something like an echo. I would never have said that myself, but okay. So, for reasons I don't know, but it has to do with the surrounding environment, I can at least go that far. Protons in different body tissues relax to the ground states at different rates, mostly because there's local fields that are affecting the ability of the spin to relax. So the scanner can distinguish between various types of tissue based on the relaxation rate, and with lots of software, and this has gotten like it's magic, but with lots of software, this becomes an image. Now, if you have a bigger B field, this increases the energy of your re-emitted signal because, of course, your spin up and spin down are further apart. This gives you better spatial resolution, shorter measurement times, and improves the signal-to-noise ratio. So, like everything, bigger is better. Well, not everything, but... So, I'm sure in Singapore, your hospitals all have 7 Tesla by now. In Gainesville, most of the imaging centers have both still, and it depends on what they want to measure, whether you get the 3 Tesla, the 7 Tesla. It's very sweet when you go in there. They talk about the high field MRI. I once, using free wire, wound my own 7 Tesla magnet. Took me 2.5 days on a lathe. I did a wet ramp, so it had epoxy on every layer, so it was rigid. I didn't kink it once, because remember, you kink it once and you're dead. I wound my own 7 Tesla magnet. It had a 2-inch bore. High field. Okay, well, whatever. There's a company called Bruker, which is based in Karlsruhe and has offices everywhere. And I don't know why you'd want to image a small animal, but I guess because you want to do research. Because there's not that big a bore. You can't stick a person in there. I would tease Marilyn, but I won't. You can't even stick a small person in there. Like I said, up to 9 Tesla, everyone uses niobium tide, and it's ductile. So, research places, like we have a brain institute at the University of Florida, which has magnets up around 11 Tesla and has huge bores so that they're very expensive because there's a lot of wire involved in having a huge bore. They're not in some hospital, but there are research magnets that have higher field magnetic fields. And so this is a huge use of superconducting wire. Huge. This is industrial strength, lots and lots of miles and kilometers of wire. So maybe this is not appetizing just before lunch, but here is a scan of a person's brain, and this contrast here, this is a cancerous nodule in the person's brain. So what you do is you get your MRI, the doctor says, okay, you have brain cancer, but it's okay, I'm a good surgeon. They know where it is, and they can go in and excise it. And unless it was an important part of your brain, you're fine. Now, if it's your speech center, your sensory center, your memory, but there's lots of parts of the brain that they haven't quite figured out the uses for, and mostly a little nodule like that, you're good to go. Unless it metastasizes and then applications are practical. Magnetic levitation, let me just show you what it works. You know, here's your superconducting magnet, the South Pole. Here's your superconducting magnet, the North Pole. Here on the track, which you're busy zooming along, are a bunch of superconducting opposing magnets. And so, you know, like poles repel, so you levitate off of here, you use some phasing to pull yourself forward, and it leaves aside the mechanical wear and tear that you get by having wheels and axles on a track. So for instance, one of the times my wife and I flew into Germany, we had a high-speed train connection at the Frankfurt airport, and we got there and our train was 4.5 hours late. Why? Because the German rail system had discovered the day before that all of their high-speed trains were about to fail, and so they took each and every one out of service, put it up and looked and saw if there was any sign of fatigue on the metal parts, and those that didn't show any sign of fatigue went back in service. So ours went back into service and was only 4.5 hours late, but lots of them were taken out of service, so the board that you looked at in terms of trains coming is like 2/3 canceled, right? So there was a day in Germany where high-speed trains didn't exist because of all the mechanical fatigue. You know, if you're going a couple hundred kilometers an hour, which those trains routinely do, there's a lot of mechanical fatigue. Not if you levitate. Okay, that goes away. You put this thing in a vacuum tunnel and you can go really fast. Okay, so here are some examples, and I confess I didn't spend months preparing this slide. I spent about 4 hours. I don't know what kind of magnets are in this. My guess is these are normal state magnets because this was made by a German company called Transrapid, and at the cost of over, I think, 1.2 billion US dollars. And I'm pretty sure Transrapid uses normal state technology, but it's really fast. Okay, and it's in commercial operation. It will take you 30 kilometers, and it will go from Shanghai airport to one of the metro stations. I mean, you can ride it. It's not a toy. It's actually in useful operation. Okay. Now here's a toy. Japan wants to prove that it's better and faster and etc. And they have a liquid helium temperature superconducting maglev that has the world record for train speed. And of course, it's just a toy. It's you know, a little over a mile in length. And they're planning on doing commercial service now. This and 50 cents will get you a cup of coffee. Planning anything 9 years in advance, I wouldn't buy stock. You know, it's like when you're building something, like there's all these buildings the U.S. puts up. If you go to the site engineer and you say, when's it going to be finished? And he says, today, it'll be finished in a year. If you go back in a month and you say, when's it going to be finished? And he says 11 months, you can start believing it. But if he says it's going to be finished in a year, then you know it's a theoretical answer, right? And my guess is if you go to the Japanese and you ask them each year when is the due date, it's going to be put back a year. Because it's not commercial, okay? It's slightly better, it saves you some maintenance, it's not commercially viable, all right? The Chinese did it because they wanted to be the biggest and the best. The Japanese are doing it because they want to be the biggest and the best. It's not commercially viable, as will be many of the applications that I wind up to talk with. This is sort of your fairy tale before you have lunch and take a nap. This is fiction what we're talking about. There is one in South Korea that I never knew about, even though I've been there since then, and it's a low-speed track, and again, it's a proof of possibility thing. Okay, so here is the U.S. Armed Forces. Nothing is too good. I never knew this, but in researching weird applications to keep you guys awake at the end of the talk, I found this one. So everyone knows what degaussing is. Something is magnetized, and if you twirl it around in a constantly increasing or decreasing field, you can demagnetize demagnetize or degauss, that this just means demagnetizing something. So it turns out the US Navy, I did not know this, degausses their ships. Who knew? And so all of these ships have tons and tons of copper wire running around them, a network of electrical cables installed around the circumference of a ship's hull, inside the hull, because you don't really see it, running from bow to stern on both sides of the vessel, and they degauss their ship. So A, it's harder to see with a magnetic sensor, and B, magnetically activated mines won't come rushing up against the hull and go boom. I never knew this. So you can, of course, avoid this by making a non-ferrous metal boat. The Russians did this once. It was the most expensive boat ever made. It's a submarine. It's now been deactivated and chopped up into component parts. And it was made out of titanium. And you can read about this titanium submarine in one of Tom Clancy's books. I'm told by reading that inside the Russian Navy, everyone hated this thing because it sucked up all the research money for years. And it's unaffectionately known the golden fish due to its cost. So it cost essentially like it was gold. So that's not a proper suggestion. People are going to be degaussing their thing. Now the other thing is that I haven't talked about in any of these slides is in 2009 the Navy tested a 37,000 horsepower superconducting engine that has more torque, weighs less, is more reliable, and is quiet as heck on one of their smaller naval vessels. And it was successful. So there is a news article saying from the company that made the wire for the superconducting motor that it was successful. And since 2009, I can't find a reference. Now, if it worked, and it had all of those properties, plus it made it harder to detect, I'm a little curious why we haven't heard why there's more of these things. I don't know. Two possibilities. It's too expensive. You're all going to laugh now because for the U.S. military, that concept doesn't exist. Or it's classified. And some idiot let it out of the barn before they were told, no, don't publish that. So anyway, it may be that U.S. ships are running around with superconducting motors. There's at least one. So here's some more advertising words. Here are, and they're made out of high temperature superconducting material, which I think is pretty interesting. For these things, for the degaussing, they're made out of high temperature superconducting wire. Now here's another one of these fables, one of these stories. Can't we save the energy losses in normal conductor power transmission by making the transmission lines superconducting? Answer, yes, of course. And it's 6% in the United States. We have a rather efficient energy grid, as long as you leave Puerto Rico out from the discussion. That was a joke. And 6% of the cost of the cost of the power, I mean, it's billions of dollars. So the answer is you could save money if you could put power cables up there. And I've been in groups where there were contracts to develop conductor for power energy transmission, and it's just not going to happen. Rare earths are too expensive for second generation. Silver tubes are too expensive for first generation. You need to invent a superconductor that's a little better than what we got. Because remember, those power lines are mostly AC. There is a DC power line in the world. I think it's in South America somewhere. But mostly these are AC lines, and there are going to be AC losses. And it's just really hard to hang a wire up between towers and have a cryo cooler keeping the wire cold. It's really hard. So you could do underground power transmission, which is what you'd have to do. It would be really expensive. So there is a demonstration cable in South Korea, and it works. Of course it works, but it's expensive. Now here is one that's a real fable. This is a real fable. You guys don't have hydroelectric power in Singapore. You have no tall mountains and rivers going over them and falling down and running hydroelectric generators. The United States has something like 15% of their energy production from hydroelectric power plants. They have a lot of water flowing over cliffs and going down through generators. There's one at Hoover Dam, which is near Las Vegas. The United States does a lot of this. So you may notice that at night, you go to bed, you turn your lights out. Air conditioning necessity, although in Singapore it's not a big change, is less because it's a little cooler, only a little in Singapore. But in most countries it cools off a lot at night. Industries don't work at night, mostly, et cetera, et cetera. So the energy needs at night are much less. Well, what are you going to do with the power generated at the hydroelectric plant? Right, the water falls 24 hours a day. It doesn't stop because you say, hey, I don't need that power right now. Could you keep the water up there? And it generates the electricity. So where are you going to store the electricity? So one of the suggestions is get a huge honker superconducting magnet, huge, and store the energy there overnight. Draw it out in the daytime. It's totally economically unfeasible. Totally economically unfeasible. I will tell you what the United States does now. Do you know what the United States does with its hydroelectric power generated from dams that generate electricity at night? They use the electricity to run water pumps. They pump the water back up the hill. I'm not kidding. That's what they do. Because otherwise, the energy is lost. I mean, you might ask, where is it the United States refines bauxite ore to make aluminum, which is a huge cost of electric energy? Where is it they do that? They do it in the Northwest, where there's a bunch of hydroelectric power, because energy is cheap. Water falling over a hill doesn't cost very much, right? Solar costs a lot, nuclear costs somewhat, coal-fired, gas-fired, it all costs money. Water falling off a hill doesn't cost much. So all of the bauxite refining factories are up in the Northwest where the power is cheap, and they have a bunch of water pumps that pump the water back up for the energy that's not being used. You can Google that, it's a true story. It sounds stupid, but it's a whole lot less stupid than making a huge honker, hugely expensive superconducting magnet to store energy. No one's convinced the Department of Energy to fund this past the let's take a look stage. No one's actually gone off and done this, which is saying something for the contract monitors. Fault current limiters. So you have a wire and it's carrying current, and suddenly it's carrying too much current. So there's a short to ground somewhere in the line up ahead, and it's starting to draw too much current down the wire. That's known as a fault current, and you want to stop that. So putting a superconductor in series such that when the current gets above a certain level, you've exceeded the critical current and it goes normal, and it's like a switch that opens, boom, there's no more current, or not much current, because the resistivity of a superconducting material in its normal state is typically very high. It's not like gold or copper or something where the resistivity at low temperatures is low. The resistivity at low temperatures above the transition temperature for superconductors is typically rather large. So it's like you open a switch and the current stops. So this is actually not a bad idea. And there are fault current limiters in use. Forget about DC, we need an AC fault current limiter. And of course, because it's AC, you've got your flux lines moving around, and you need some cryogenic helium. If you were going to use the low temperature superconductors, so that's uneconomic. So you need the high temperature superconductors. And that's actually being done. So that's a quick look, and I'm 4 minutes over, of applications. Next time, we'll talk about layered dichalcogenides, which were the first and still popular molysulfide, still popular two-dimensional superconductor. Thank you very much. And of course, I'm supposed to ask for questions. if it's like last time, no one has one.